Okay. The word titration. Titration refers to a process in which the reactants are reacted together and we identify the end point of the reaction, meaning the point at which the reaction gets completed. So it's a process in which the reactants react, and it's a process which is used to identify the point or the instant at which the reaction gets completed. So in short, we understand when the reaction is completed through the process called titration. Now to understand the basic setup, titration mein, let's consider there are two reactants, R1 and R2, and they react together to form the products. So the reactant R1 is, let's say, a standard solution. A standard solution is that solution, the concentration and volume of which is known and it is fixed. The standard solution is a solution of which the concentration and the volume is known and it is fixed. We call it a standard solution. And the R2, the other reactant, it is any solution of known volume. The volume would be known of this solution, but the concentration would be unknown. And this is what we will be finding through the mathematical equation we get by the process of titration. Now, experimentally, this standard solution is taken in a burette, and the solution of known volume is taken in a conical flask or the titration flask. So as you see the setup, this is the burette wherein the standard solution is taken. Okay. This is the burette where the standard solution is taken, and this is a conical flask where the solution of known volume is taken. Now, the burette solution is referred as the titrant, meaning the R1 is basically called as the titrant, and the R2, the solution of known volume taken in a conical or the titration flask, is called as the analyte. So basically, here we are analyzing the unknown concentration of the R2 reactant. So now the would be burette would be putting the drops of the R1 into the analyte, and there will be a point where the reaction will come to completion. So the point where the reaction comes to completion is called as the end point of the reaction. As the word suggests, it is a point at which the reaction ends, end point, and this is also called as the equivalence point. Again, as per the name, this is a point where equal amount of reactant R1 and R2 have reacted and the reaction has reached the point of completion. Now, at the equivalence point, we say equivalence of the R1 would be equal to equivalence of R2. This is the point where equivalents of the R1 and R2 become equal. Now, what is equivalent? For that, we will understand through the concentration concept. So as we know, molarity is measured by the ratio of number of moles upon the volume of the solution in dm cube or liter. Through this, I can say number of moles is molarity times the volume. Now, the equivalence point of equivalence is abbreviated by EQ, and it is given by number of moles times the n factor, n into n factor. And from the equation 1, the number of moles is molarity times the volume. So equivalence का formula बन जाता है molarity into volume into n factor. And n factor is something which we have already discussed for acid base and redox reaction. So the only thing, the hero of the concept of equivalence is n factor. So now going back, if I talk about the equivalence of R1 and equivalence of R2, I have to just equate the m into v into n factor of the R1. So let me call it as m1 v1 n factor of 1 equal to m into v into n factor of the reactant 2. So let me call it as m2 v2 n factor 2. So this is the mathematical equation we will be using to calculate the unknown concentration or maybe the unknown volume or any of the parameter out of which the data is asked. Now let's understand this equivalence concept for the acid-base reaction. So for the acid and base, we had the example of H2SO4 reacting with NaOH. It can produce two types of salts. So let's say in the ratio 1:2, they react to give you Na2SO4, sodium sulfate, and water. So we know that the N factor of H2SO4 is 2, and the N factor of NaOH, irrespective of whatever salt formed, is always going to be 1 because it's a monoacidic base. So in this case, M of the acid into volume of the acid into N factor would be 1, sorry, N factor would be 2 is equal to Mb into Vb, molarity and volume of the base into the N factor is 1 on this side. So what I've done is I have equated the equivalence of the acid sulfuric acid to the equivalence of the base sodium hydroxide. So that's what we do in the acid-base neutralization. Now, in the case number 2, that is for the redox reaction. So take any redox ka example. Let's say we have permanganate reacting with oxalate to give Mn2 plus when the medium is acidic, along with that CO2, that is carbon dioxide. Now for this redox reaction, if I talk about the oxidation states, permanganate has Mn plus 7, oxalate carbon plus 3, Mn is plus 2, and carbon is plus 4 in CO2. So for this reaction, Mn, if you observe, is undergoing reduction and carbon is undergoing oxidation. So this permanganate is an oxidizing agent and the oxalate would be reducing agent. So at the point of completion of reaction or at the end point, I can say equivalence of the oxidizing agent, is equal to equivalence of reducing agent, meaning the equivalence of permanganate MnO4 minus is equal to equivalence of oxalate C2O4 minus 2. So through the formula, molarity into volume into, now N factor for the permanganate is the change of 5 times the number of atoms, which is 1, it equals to M2 into V2 into N factor. Carbon is changing from plus 3 to plus 4, so change is 1 times the number of atoms is 2. So now we have the data of M1, V1, and let's say M2. We can find out the volume V2 through this mathematical equation. And that's what the application of titration is. Now, the concept of indicating the endpoint. So endpoint would not be observed through the naked eye. So we require some external chemicals which are called indicators. And the indicators will indicate the endpoint of the reaction through the color change. Now for titration of redox reaction, there are various redox indicators which are used. First, permanganate. Permanganate is a self-indicator. Self-indicator matlab, it will indicate the change or the endpoint on its own, meaning no external chemicals will be required. Permanganate as the oxidizing agent shows a color change from intense purple to light pink. So इसमें कोई external chemical की जरूरत नहीं है. Directly the intense purple to light pink color change indicates the end point of the reaction. But for the dichromate or the other oxidizing agents, we require the indicators. So it requires the indicators to indicate the color change. So for them, we have two main types. The first one is internal indicator, and the example of internal indicator we have is diphenylamine or N-phenyl anthranylic acid. N-phenyl anthranylic acid. So they are the internal indicators which are used in the dichromate titrations mainly. And secondly, when we talk about external indicators, so external may we have the example of potassium ferricyanide with the formula K3FeCN6. And for the reactions involving iodine, we have the use of starch indicator, where the blue color of the iodine will be changing to black or brownish black. So that is mainly used for the iodine reactions. Also, remember for the titration involving the Mohs salt, which is the ferrous ammonium sulfate, having the formula FeSO4 dot NH4 twice SO4 dot 6H2O. For the ferrous ion estimation or the Mohs salt reaction, there's only ion changing from ferrous to ferric. So in this reaction, if we talk about the N factor involving the Mohs salt, it is to be taken change of 1 into the number of atom 1, meaning 1. So Mohs salt related any reaction, if you are asked equivalent mass, then it will be molar mass upon the N factor. So this is all about the redox indicators which are commonly used in the titration of redox reactions. Lastly, the reactions in which the oxidizing agents are used as the reagent, oxidizing agent, we have a fixed change in the oxidation number. That's why the N factor of these type of reagent always remains fixed. So we have permanganate as a very common oxidizing agent in many reactions. Permanganate can act as the oxidizing agent in various mediums. So there are three cases in which the product of the reaction differs. So of course the N factor differs for different medium. So permanganate in acidic medium, meaning when there is H plus ion, changes to the product of Mn2 plus. The change is 5 times the atom is 1, N factor is 5. The same permanganate when reacts in the weakly alkaline medium, meaning when the medium is basic and weak, which is equal to the medium being neutral, only the water involved, no H plus or OH minus. In that, the product is manganese dioxide with the change going from plus 7 to plus 4. So change is 3 times 1 and factor is 3. The same permanganate, if you react in a strongly alkaline medium, changes to manganate ion MnO4 minus 2, where the oxidation number changes from plus 7 to plus 6. The change is 1 times atom is 1. So you see the N factor is 5, 3, 1 respectively when the medium is acidic, weakly alkaline or neutral, and strongly alkaline. Lastly, the other common oxidizing agent is dichromate Cr2O7 2 negative. Medium only acidic, change to 3 plus. So here the dichromate ka chromium changes from 6 to 3, the change is 3 times the number of atom 2. So the N factor is 6 and that is fixed. So there's 4 cases of the permanganate or dichromate acting as oxidizing agent. If you know the N factor is the same throughout, you can calculate the equivalent weight in any of the medium as given for permanganate or dichromate. So that is the summary for the common oxidizing agents. With this, we complete the redox reaction with the last part of titration and the concept of the N factor used for oxidizing agents. Thank you.